Flow separation. A CFD tutorial prepared for undergraduate fluid mechanics students to spend some valuable time during the COVID-19 outbreak. Here is how the drag coefficient changes with the Reynolds number for flows over cylinders and spheres. As you may remember, in the previous video, we solved the creeping flow over a 2D cylinder at Reynolds number 0.4, and obtained a flow field that looked like this. In this video, we will solve the same problem at Reynolds number 40, which is 100 times higher than the previous one, but still a very low value compared to many practical engineering applications. At Reynolds number 40, flow field is expected to be like this one here. The main difference with the previous one is the boundary layer separation and the circulation bubble in the wake. Go to the folder where you saved the previous ANSYS simulation, and find the ANSYS Workbench project file, with the extension WBPJ. Double-click it to start the workbench. If you do not have a properly saved project file of the previous solution, you have to recreate it. Here is our previously saved project. Make sure that the geometry, mesh and setup cells have green check marks next to them. Double-click the setup cell to start Fluent. A warning message will pop up, saying that the previously generated results will not be visible, which is not a concern for us at this point, because we will resolve the problem. Click OK. Also click OK on the Fluent launcher. The triangular mesh that we created earlier should be visible. Let's first make sure that the fluid properties are the same as how we set them. Under Materials and Fluid, double-click Air, and see if the density is 1.2, and the viscosity is 1.8 times 10 to the minus 5. To increase the Reynolds number 100 times, we can increase the inlet velocity 100 times. Under Boundary Conditions, double-click Inlet Velocity, and increase the magnitude to 0.6 meters per second. In order to be able to calculate the drag coefficient properly, we need to change the reference speed also. Double-click Reference Values, and change the speed to 0.6. Make sure that the drag coefficient report that we created in the previous project is still available. Right-click Initialization, and initialize the solution. Press OK, if a warning window about the loss of previous data pops up. Double-click Run Calculation. With maximum number of iterations set to 1000, press the Calculate button. You will see how the drag coefficient changes with iterations. The solution will converge in about 50 iterations. The converged drag coefficient is about 1.54. This drag coefficient versus Reynolds number plot gives a value between 2 and 3 at Reynolds number 40. But the value we got in our simulation was 1.54, which is at least 40% off. Let's compare our result with other references, such as Schlichting's classical boundary layer theory book. Schlichting's book has a very similar plot to that of Munson's. At Reynolds 40, drag coefficient is between 1.5 and 2, which is much closer to what we got. Let's double-check this value with another reference, which performed numerical simulations like us. Here is one, from 2009. They performed simulations in the Reynolds number range of 6 and 40. Here is their drag coefficient result at Reynolds 40, compared with other studies. The values are quite close to the value of 1.54 that we got. Here, we are back at ANSYS Workbench to perform some post-processing. Let's start by plotting static pressure contours. Static pressure variations are very localized around the cylinder. Being a higher Reynolds number flow than the previous one, we expect to see more localized viscous effects and boundary layers. Highest pressure is seen at the front stagnation point. Pressure on the surface of the cylinder decreases up to a certain point, seen here in the darkest blue color. This part has favorable pressure gradient. But then, surface pressure starts to increase slightly. This adverse pressure gradient region is where we might have boundary layer separation. To see the minimum pressure point on the surface better, change the contour coloring option to banded. Here is the minimum pressure point on the surface. Before this, there is favorable pressure gradient, and after, there is adverse pressure gradient. Let's see the variation of pressure over the surface on an XY plot. Under Results and Plots, double-click XY plot, and select Circle as the surface. By default, pressure over the cylinder is plotted with respect to the x-coordinate. Diameter of the cylinder being 1 mm, minus ½ mm is the front stagnation point, and plus ½ mm is the back of the cylinder. Gauge pressure with respect to the zero outlet reference pressure, varies from 0.25 pascal at the front of the cylinder, to a minimum of minus 0.2, at about its center line, and increases again to about minus 0.1, at the back. Favorable and adverse pressure gradient sections can clearly be seen here. To see if there is any flow separation or not, we can have a look at the path lines. Let's first create a vertical line upstream of the cylinder to release the path lines. Under Results, right-click Surfaces, and select New, and Line Rake. Change the type to Rake, and set the number of points to 30. This will allow us to release 30 path lines from the line that will be created. Set the endpoint coordinates of the vertical line as shown. This line will be 1 diameter in front of the cylinder, and its length is also 1 diameter. Double-click Path Lines. Select the newly generated rake. Change the color parameter to Density, to have constant color path lines. Select Mesh to make the cylinder visible. And display the path lines. As you see, there are some unexpected kinks in certain locations. This is a visualization artifact, and can be removed by changing the step size, used in creating the particle paths. Decrease the default step size 10 times to get rid of them. As seen, streamlines cannot follow the contour of the cylinder all the way to the rearest point, but they separate. To see the details near the separation point better, add the circle to the surfaces from which path lines are released. And animate the path lines using the pulse button. Separation point is now seen clearly. And there is backflow after it. Vector plots can also be used to feel the circulation region better. Double-click Vectors. Change the vector style and scale. Zoom out to see the big picture. Zoom into the separation region. Increase the scale to see the vectors better. And have a look at the circulation region. There are two counter-rotating circulation bubbles at the wake of the cylinder. Let's check the velocity profile above the cylinder. First, create a vertical line above the cylinder, that goes from the shoulder of the cylinder, all the way to the outer box. Enter the endpoint coordinates of the line as shown. Double-click XY plot. And plot the variation of x velocity over this newly created line. Set the y variable as the y coordinate, and the x variable as the x velocity. The velocity starts from 0 on the surface of the cylinder and very quickly reaches its maximum value of about 0.7 meter per second. Then gradually decreases to the free stream speed of 0.6 meter per second. To see the details inside this region close to the cylinder better, we need to change the length of the line over which we plot the profile. Let's decrease the line length by 10 times. Under Surfaces, edit this line called line 7, and decrease its endpoint y coordinate 10 times. Update the XY plot. Here we can see that maximum speed above the cylinder is reached at y is equal 1 mm, a distance from the surface of about 1 cylinder radius. Here we compare the velocity profiles above the cylinder, for our earlier Reynolds number 0.4 simulation, and the current, Reynolds number 40 simulation. For the lower Reynolds number case, maximum x velocity seen above the cylinder is reached at y is equal to 15 mm, which is 15 times the cylinder's diameter. But for the higher Reynolds number case, maximum speed is reached only at about 1 mm. This clearly shows how boundary layer gets thinner as the Reynolds number increases. Now try to imagine a much higher Reynolds number case, such as 100,000 or a million, which are typical values for many practical problems. At such high Reynolds numbers, boundary layers will be extremely thin. It is also important to note that, for the creeping flow case, the free stream speed of 6 mm per second cannot be seen even at the edge of the outer box, which is at a distance of 40 cylinder diameters. But for the higher Reynolds number case, free stream speed can be reached much closer to the cylinder. We can finish post-processing by reporting the pressure and viscous components of drag. Under Reports, select Forces. And report the drag force acting on the cylinder. Forces are low, due to the very small diameter of the cylinder. But what we are interested in, is the percentages of pressure and viscous components. Pressure component is about twice of the viscous one. If you remember, they were about the same for the earlier 0.4 Reynolds number case. Boundary layer separation, seen here, did not allow for good pressure recovery, resulting in lower pressure at the back of the cylinder. And this low back pressure increased the pressure drag. Let's finish this video by comparing the drag forces of the two Reynolds number simulations we performed so far. As the Reynolds number increased 100 times, the drag coefficient reduced 14 times. In the meantime, the drag force increased 700 times. This may at first sound confusing, but a decrease in drag coefficient does not necessarily mean a decrease in drag force too. Remember the relation between the drag force and the drag coefficient. Density and the reference area of both simulations are the same. The difference is the 100 times larger speed in the second one. As the speed increased 100 times, even though the drag coefficient reduced 14 times, the force increased 700 times. When you compare the drag forces of two different Reynolds number cases, it is important to know how the Reynolds number is changed. Is it due to speed change, or viscosity change, or maybe diameter change. In each case, the change in drag force would be different. But, in all those cases, the change in drag coefficient would be the same. That is why, reporting the drag coefficient, instead of the drag force, is more logical. One should always calculate the drag coefficient first, and then switch to the drag force if necessary. In the first case, pressure drag was half of the total drag. But in the second case, pressure drag becomes more dominant, and it is now 67% of the total drag. And with this comparison, we are going to finish this tutorial. In the next one, we are going to modify the geometry, by extending the rear part of the cylinder, to give it a more streamlined shape. With this change, we are hoping that the magnitude of adverse pressure gradient can be lowered, and separation can be avoided, resulting in a decrease in drag.